Hello, I'm MC Punchy, the second worst rapper in the world, and today we're gonna look at what? Uh, oh, I thought it'd be fun. Okay.
Hello, I'm MC Toon, the worst rapper in the world. Punchy, I don't know what he's doing. Had to take care of some business there, so dealt with that. So, welcome. Today, got a special treat. It's earlier than usual, and that's because we've got some Gleem action, who's in the UK and didn't want to wait until 1 a.m. So we've got Gleem and Jack Zhang. How are you two guys doing?
All good, salute. Welcome one and all.
Yeah. And Jack, how you doing? Oh, I think you are muted, Jack. So I don't know why I could hear you before, and now I can't. So
It's not because I muted myself, was it?
No, I don't think so. I don't see any volume bars on his thing there. So something's going. Yeah. Match Rocket is asking, did everything come out okay? Yeah. Punchy did. He started it just fine for me there, and
Oh no.
there. Hey, we can hear you, Jack.
There we are.
How you doing?
I'm all right. Just moved back though, so I'm tired.
Yeah, move back to
Back to London.
London. Now that's not the London near Gleam.
No,
That's
London, Ontario.
London, Ontario.
It's not the London blood, it's the London. I don't know how you say it. It's pretty rubbish, really.
So we've got two topics today. It's gravity and perspective, and both Jack and Gleam, they're going to discuss it. I'm just going to moderate and facilitate. But first, I'd like to give a chance for both Jack and Gleam to introduce themselves and say what they want to say before we start it off. So go ahead. Let's. You want to start, Gleam?
Sure. Hi, I'm Gleem. For those that don't know me, I'm sure half the chat already know me, and they've already told you about me anyway. But I am what's known as a non-flat earther. However, I am a flat earth sympathizer. So I'm a non-globe earther as well. I just put it this way. I always describe it as there's a blue team and a red team, and I'm just here watching the match
Sure, you're
and
not
enjoying
purple.
it.
You may be purple
No.
team.
I don't wear them colours. Although they are royal, but beggar in purple cloth, obviously. But anyway, so I am here to defend the flat earth, albeit I am not a true believer of the flat earth. However, I do believe that the topic has sparked up a interest in science, and it's taught me a lot about science, or made me want to look into it. So I commend it for that, and I give it the respect of the giving it the time of day, entertaining the thought experiment, let's say. And there's a few questions that I'd like to ask, and I'm pretty excited about this one. I'd like to ask Jack because fresh mind, well educated, and I'm sure he's going to school me on a few things.
All right, Jack. What do you have? You got an introduction? Let us know who you are. You're kind of new, so more information
Well, I
is
was
better.
here last time, but for those who don't, I'm Jack. I'm a mathematics physics major at University of Waterloo. I'm just here for the hell of it because I do find this stuff interesting to debate. Um, I suppose that's all I got for an introduction, but I do have something to say because last time I did make a few statements that were erroneous, and I should correct them. So I said that if a plane's autopilot had failed, they would probably just land it, because I assumed that if something were to go wrong with autopilot software, that would signify something wrong with the entire flight computer. Apparently, that's wrong. Pilots will still fly manually long distances, albeit they do admit that it's not as efficient as flying with an autopilot, but the difference is basically negligible as far as they're concerned, and I didn't realize that. So I recant what I said earlier on the earlier thing.
All right, thank you. So Jack, your volume is a little low. So if you can do something to turn up your volume, that'd be good. And they're saying mine is too quiet as well. So maybe Gleam, you could turn your volume. You got a fader on your
Down.
neck. Maybe you could.
No, I've got a nice preamp here that will.
Oh, there you go.
Okay, how about now? Little louder? Or...
Yeah, that sounds a little better.
Am I like? Are you a little lower?
You could go a little more, Gleam.
Okay. Just say it. Just say I'm a big mouth.
All right.
Okay. I've just done 2 decibels. Is that all right?
I think that's
Is that right?
better. And what do you say,
Yep.
Jack? Let's see, Jack.
All right, how about now?
There we go. I think you're both about the same on my my meters here. So I will. I'll let the two of you go, and I will after a while, about halfway through, I'll interrupt and we can switch topics.
Sure.
All right. Gleam,
Can
it's all you.
Yeah, I was going to ask to take the lead, and I will say salute straight away, Jack. You know what I mean?
All
It
right.
takes a man to actually admit some mistakes, even though, in my personal opinion, mate, that isn't actually a massive mistake. If computer systems do go down, okay, yeah, you would go on there, but I would assume the same. I would assume the same. They'd go into the next landing for the next airport. We can't fly over the Atlantic with no. Anyway, getting on to the topics. The reason why I've chosen these 2 topics is that I believe that there is a lot of topics out there that are argued endlessly in this debate, and they're basically cross model compatible arguments. Where I started this off and stated this when I first had a debate with MC2. Both me and you, Jack, we could end up on a thought experiment. This is, we could end up stranded on a deserted island. Okay, we have no memory of what we've been taught, what we know. We obviously set up camp. We survive for years. We do whatever. You have half the island. I have the other half. One
Right.
day we're sat there having a conversation, and you say to me, "You know what? I've been looking at these stars, and the stars seem to move." Now, I don't think, even though it all looks flat, I don't think that we actually live on a flat Earth. And I'd probably go, "What? It looks flat. Don't be stupid." And you'd go, "No, wait there. Let's try and find out what the shape of the Earth is." And if you took on the role of, "Yeah, I'm going to figure out all the stars, count them, do the shadows with the sticks, do whatever," and you can formulate a working globe Earth model based on the observed reality that you just built it from. Yeah. But me on the other side of the island can adopt the opposite thought and can build a model which represents the same reality that you're seeing, yeah, but on a flat Earth model. Okay, so I believe that from that standpoint, there's a lot of things like, put it this way. I mean, a motherboard in a computer doesn't need to be aware of what the shape of the Earth is, so you can't really say, yeah, a motherboard debunks a flat Earth. So and there's a lot of people who in the globe Earth side who do say, no, you'd have to change the whole of physics in order. All physics laws must change. When you look into it, and I'm sure you're fully aware of general covariance, where and scale invariance, where all laws of physics have to work everywhere. Yeah, if there was, even in a globe Earth universe, even if there was a flat planet that was discovered, I mean, they had that cigar-shaped one. Why not a disc-shaped planet that had all formed and into a disc? The laws of physics would still have to work the same on that disc as it does that we formulated on the globe. So, yeah, I say the 2 core factors, cutting to the chase because I'm a babbler. The 2 core factors are gravity and perspective. Obviously, gravity is a huge core component of the globe model, and perspective is a huge component of the flat Earth model. Now, again, these can be argued endlessly, but I do believe there's valid discrepancies with gravitational theory enough to question it. Yeah, and I do believe that perspective does have validity to it in order to explain blockage from the bottom up, which can actually then connect into how sun sets, how you can't see Polaris past the equator, etc., etc.
Okay.
So I'd like to start with gravity, if we can. Now,
Right, shoot.
yep, go on. Sorry. Were you saying something then, or did you drop?
No.
No. Okay. Sorry. Yep. So, as I say, there's a thing that I've, so to say, coined called the flock-mock paradox. And I look, as I say, I'm a bystander looking in, and I'm entertained by the debate. But what I see is a lot of globe earthers saying a lot of untrue things. A lot of flat earthers, obviously, saying a lot of untrue things. It's a human trait. It's not a flat earth or globe earth exclusive thing. But there's a core thing where if a flat earther come to you and said, I know the earth is flat because I've got a P900, I can see way too far than what the globe geometry dictates we should. Therefore, it must be flat. All blockage is due to this perspective and refraction, not physical curvature. And then obviously a globe earther would turn around and say, you idiot, you're using such small scales and there's refraction which is affecting it. The earth is so massive that when you measure it on a larger scale, you're proven that you're wrong and that you need to account for this curvature or your maths messes up. Now, in the same conversation, I see globe earthers saying, we know the earth is a globe because we've got gravity. Gravity works. It's tried and tested everywhere. It works. You can just drop something. Voila, it works. And gravity made a sphere. So it's definitely a sphere because I can prove gravity to you right now and you drop something. And then a flat earther has an equal right to say, you idiot. The actual gravitational theory is so ambiguous. It's one of the most unknown theory, albeit the effect can be calculated of the concept, but it's found many discrepancies on the same thing of scale invariance, where you take this gravity that we formed based on the solar system and you try and use it in the extremes of the universe. It doesn't work. You take it down extremely small, it doesn't work. It's incompatible with the quantum side. So there are failures, there are exceptions to the rule. Let's say if those didn't exist, then there would be no question. That's a law of physics. Can't question it. But I believe you can question it, and I believe flat earthers have a right to say, "Nah, gravity is nonsense." So getting into the first question that I had for you is the conservation of energy.
Okay.
Okay. So thought experiment.
Sure.
You've got a human, a brick on the floor. You've got air pressure in a sealed system. Basically, let's just forget about everything outside. We are measuring the energy input and output of this system. This
Give me
net
1 second,
system.
just so I can
Sorry.
pull up a visual here. Give me 1 second.
Sure.
All right. Sure. You guys see my page or?
Yeah, I can see you.
Okay, so here, let's do this. Shit, oh, for fuck's sakes.
Beep. Sorry, the actual censoring system's going a bit messed up. Coronavirus, obviously. I will actually say, I want to take a moment of silence for everyone who's passed away through this coronavirus. It's a nasty thing. Salute. Okay.
So you got a guy in a sealed system with some brick.
Yep. Some brick on the floor at rest. Yeah. Whatever it is.
All right, keep going.
Okay. So I say that we are concentrating on that brick, what that brick is doing. Okay. And what makes it move, what makes it fall and drop and accelerate. Okay. So the first action is you moving up to the brick and resting your hands on the brick. Now, as you're fully aware, and I'm so happy you're qualified and you can school me on this, but I'm sure you're fully aware that the electrons in your fingertips will not allow your fingers to go through that brick because they resist the electrons in the brick. Okay. So we do not care about any energy up until the point of you connecting with that brick. Therefore, it's all energy loss. So that human walking up to the brick and touching the brick, forget that. We are on about this point and this point onwards. Okay, now the human needs to put into the system force enough to equal and more and overcome the weight of the mass. Yep.
Yes.
So you have to grip it at a certain tight. You can't just grip it loosely and pull up because it wouldn't work. You have to grip it in tight and pull that mass up into the air. Okay. Now you are the force provider, let's say.
Okay.
You have just given that brick what's known as gravitational potential energy.
Right.
And that does confuse people sometimes because obviously that stands for gravity. Okay. And from a flat earther's point of view, obviously with my flat earth hat on, this is how it works on a flat earth without the mention of this concept of an external force required. So
Okay.
you are suspending this brick, you are applying a force. When you release this force, that brick was, let's say, at rest with your force applied.
Okay.
And when you release it, it was at 0 meters per second, and it has to accelerate in order to go down. Now, the downwards acceleration and the movement towards equilibrium again, where its natural place of rest is, which was where.
What do you
Okay.
mean by return to equilibrium?
Okay. Now this is where it differs. Okay. So I've just put gravitational potential energy into that brick. I let go.
Not quite, but just go on and I'll let you finish.
Okay. Yep. So I let go and that brick falls to the floor, returning the energy, the potential energy I put in it, and it returns it and releases it all on impact with the ground. And then the brick becomes at rest again.
Okay.
Yeah. So
Sure.
that is literally the description of gravity, why it's not needed, because it's the human doing the force input. Whereas
Okay.
it's the globe earth belief, obviously, that there is an external force which is dragging that down, or obviously the earth coming up if you're talking relativistic.
So what is causing it to accelerate down without gravity?
You picking it up in the first place and creating that gravitational potential energy.
Okay,
It has to
be converted back into kinetic. So what force is doing that?
Yeah, it's you. You've just done that. You've just put that force in. As soon as you let go, that force is then in the brick, let's say, and then returns as soon as it hits the floor. Now, the
But something needs to
acceleration.
accelerate it back down for it to hit the floor, though. That's the thing.
Yes, to accelerate it, you are going from 0 meters per second, letting go, and there is an unsupported medium underneath it. So there's no force keeping it there. So it must go seek the path of least resistance to achieve rest again.
But there needs to be a force to accelerate it if it starts at rest.
The force is its natural want to be on the floor because you picked it up and took it away.
Quantify a force's natural want. And also, what do you mean exactly by equilibrium? Because that can mean a lot of things in physics.
Sure. Well, if you say that mass is at rest on the floor, that's as simple as you can put it. Forgetting obviously Earth spinning and everything like that. In relation to that person, that mass is at rest, and it's that person that has to take it out of rest in order to show and demonstrate that there is an acceleration. That person is the provider of that acceleration because it wouldn't accelerate if that person didn't do that. Or another force.
It needs to, but the person's enacting a force that's going upwards. You know, the force applied is going up, not down. So what's bringing it back down when you let go of it?
It's natural mass and how that acts. It's basic buoyancy. Yeah, the medium beneath it cannot support its weight.
Okay, what's giving it its weight though?
Its mass.
That weight doesn't change
and
throughout
how
this entire era.
Its mass and how that acts in a medium, and the medium in this case is air. Because it wouldn't fall at 9.8 meters per second in water because there'd be a resistance there. So air is a resistance in the same way.
That force is not just gravity. There's going to be another force. If it's in water, it's going to be hydrodynamic drag.
Sure, but there's air here, so that is the drag. that is, so to say, slowing it down, or if you consider it as 9.8 meters per second is the rate of propagation through the medium as a base in a vacuum.
9.8 meters per second squared is an acceleration, not velocity. Okay,
Yes.
let's just back up a bit. Do you know what
Okay.
dynamic equilibrium even means?
Explain. Do explain, because dynamic equilibrium, in as much as the Archimedes principle, yes. In as much as adding gravity, yes, I understand that. But please do write it out, because I will learn something.
All this is saying is that if you sum up all the forces, that is terrible. That are acting on an object, and if they sum to zero, that means your object is in dynamic equilibrium. So, for example, when our object is resting on the ground, there's a normal force being enacted on the object by the ground that's going up, Fn, and you have a downwards acting force, Fg. If you sum these two together, they will sum to zero because vector addition, they go in opposite directions, so that basically
Sure.
You have to apply a negative symbol to one of them, whatever you consider to be positive or negative.
Mm-hmm.
And then if you sum them equal to zero, and therefore we say that's in dynamic equilibrium. In other words, this implies
Sure.
that acceleration is equal to zero. So its velocity doesn't change if it's in dynamic equilibrium. That's all that means. An object will not tend towards dynamic equilibrium. You're thinking of thermodynamic equilibrium, which is a completely separate thing altogether. In order for something to achieve dynamic equilibrium, it just needs to have its forces summed to zero, and there's nothing that wants it to tend towards that. It's just based on whatever forces are present.
Sure. No, I do agree with that. And I think that is the thing. But the force of gravity, what you're saying is a external force, let's say. The flat Earth point of view is the mass, or basically how it acts in the medium, and that creates weight. So you've obviously got air pressure coming down on you, and then if we're talking, let's say we're talking, the air pressure is the first order effect, and I don't know whether I'm getting this right, correct me if I'm wrong, but the gravity the gravity is the first order effect, and the second order effect is the air pressure being contained by that gravity, and that air pressure is acting on that brick, pushing it down. Okay, and
you
then
don't actually need there to be gravity or there to be air pressure. You just need there to be an atmosphere of gas around you.
Okay. But how flat earthers see it is that weight is just how mass acts in a particular medium.
But you need to be able to quantify how that mass acts, though. I can't just build a plane and figure out how much lift I need by just saying it's how mass interacts in a medium. I need you to be able to quantify that for me.
Sure.
Because you have to understand, this works, right? I can make an apparatus that obeys this principle.
Sure.
If you're going to say you have something else, you need to show me how it works.
But the Archimedes principle is exactly that. There was no gravity in the Archimedes principle until the late 1600s.
That tells you what buoyancy is, but it's not going to help you out in this case, because this works even if there isn't air at all.
Okay, understood. I understand that in a vacuum, that would be the net thing of 9.8 meters per second. And obviously you have a very, 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 very slight resistance in the air. It's not that different. So that's the thing. I mean, it's fractionally different enough to be able to say, I have weight as a concept of how mass acts in a medium, and the actual equations are the same. It's just the concept is completely different.
Archimedes' principle won't help you much with force of gravity, especially when you're doing orbital mechanics.
Okay, no, I understand it's not fit for purpose for that. But in this case, in a basic terms, exactly what you've just described there is weight pushing down of itself, and the ground is stopping it from going further, basically. I mean, there is, let's say, if the medium below was less dense, let's say it was mud, over time that brick would actually slowly go into that mud, sink into that mud, which is in my eyes, that is its acceleration rate through the medium of mud. So 9.8 meters per second is just the acceleration rate in a vacuum or air. And obviously
It's in
there
a
is that
vacuum, but you need to.
fractional difference.
It's just the acceleration due to gravity. If you want to find what's the acceleration in any given circumstance, you factor in all the forces that are acting on it. Okay, so here, because you said this earlier and it's bugging me. Okay, so here,
Yeah.
what we say, do you know what work is, or how it's
Sure.
defined in physics? Okay. So what we define,
Ish. I'm not formally educated. I will say that I don't claim to be formally educated, but I know basics. Yeah.
So I'll just start with the simplest stuff. Okay, so energy, because this is a term you'll hear a lot, but people often don't know how to formally define this. Energy is simply the capacity, all right,
Mhm.
for an object. For an object to cause some physical change, which could be like a deformation or a change in velocity. Cause some physical change. All right. Now, what we define as work is the actual process of exchanging energy.
Sure.
So here's how we can go further with this. How do you do work? So you do work by applying a force over some distance. So in other words, work is equal to the integral from some starting position A to B of f of x with respect to distance. That's the formal definition of work. And so what we're doing here, if we go back to this scenario,
Mhm.
you're applying a force over some distance that causes the object to get lifted, because you need to apply a constant force, right? If you stop applying the constant force, let's say here, then if you don't apply that force, it's not just going to go off on its own, because there's still another force that's acting on that's going downwards.
Sure.
So in other words, you apply a constant force from the moment it starts to move equals whatever force you're applying. So from 0 to some height h, force you apply with respect to height. That's the formal definition of the work you're doing here when you raise an object of mass m up some height.
I think I'm with you. Yep. Yep.
Now, that energy is not stored in the system, so to speak. It's stored in what's called a gravitational field. And so the reason this matters is I can't take that object and move it anywhere I want and have it retain that energy. If it was kinetic energy, it would be an intrinsic property of that object. And so an object with 50 joules of kinetic energy, 5 meters from the sun, or in my hand as it races across or shooting across my room, it's going to have 5 joules of kinetic energy no matter what, because it's intrinsic to the object. Gravitational potential energy is different, though. So we also need to define is what's potential energy. We define it as the negative of integral from some starting position to some final position of force multiplied by some displacement dx. And there's a reason for this to be negative, but I won't get too far into that right now. So basically, when we raise this object, we generate a bunch of potential energy using this formula, basically.
Sure.
Now, that energy is stored in the gravitational field, and when you let go of it, gravity works on the object. And so that work, the second time, is going to convert potential energy into kinetic energy. So we're applying a force starting from height A to some starting position 0. It's going to be F of G, which is the force of gravity, dot dH. And that converts that potential energy back into kinetic energy, which when it hits the ground, it's going to be converted into deformation or heat energy, basically.
Yeah.
Because you can't increase or decrease the amount of energy that's contained within the system without interacting with its surroundings. And so what's happening here is this human, he's using his muscles to convert chemical potential energy into gravitational potential energy by raising it. And then when he lets go, gravity does work by accelerating the object downwards.
Okay. So that's the thing. That is the exact thing which I'm not actually getting.
Okay.
The energy you have put into the system.
You're not putting it into the system because you're already part of the system.
Okay. I think I understand that. Yep.
Like you'd be putting energy into the system if it was coming in from outside, but it's not. It's
Okay.
starting from within the system already.
I think I meant to say the brick.
Okay. Again, you're not putting potential energy into the brick. You're putting it into a gravitational field.
Okay, yeah, I fully understand that, but from a conceptual point of view, it's actually air pressure.
No, it's not. There's no factor of air pressure in this equation.
Understood. No, I understand that. It's just that is the second order effect put it this way. Going back to your book where you dropped a tissue.
Okay.
Yep. What I believe you've done is what's known as a ringing gauge block.
A what?
A ringing gauge block. Now, forgive me if I'm mispronouncing that or anything, but when you remove the air gap, if you had a polished metal bench and you put a polished metal brick on there, you're removing the air gap, and you'll find that you can't lift the brick directly up because
the reason you can't move things up
slide
that
it off.
stick together, and I think a much better example would be glass slides. So if you ever work with a microscope, you have to put something sandwiching between glass slides. And if there's nothing in between and you stick these together, you can't pull them apart. That's not due to a lack of air pressure, mind you. That's due to what's called a London dispersion forces between the molecules that are basically on the surface of each glass surface that are in contact with each other.
Okay, so that's an electron thing rather than that, because obviously with a ringing block, if you look it up on Wiki, it's up on Wiki as the thing. What they do it as is two smooth bricks, metal bricks, basically, and you can put them side on side and they won't slip off. But their explanation there is that what's happening is you're removing the air gap, and because there is a ton of pressure acting on all sides, I don't know whether that's correct or not. Correct me if I'm wrong. A ton of air pressure acting on all sides. You're removing the ton of air pressure applying on that side of the internal side of each brick. Therefore, they stick together. Is that an incorrect understanding? And it is London forces, as you say.
It's mainly London dispersion forces. I mean, sure, there's some force that's sandwiching these together, but that's easily overcome by just applying a force that's greater than that.
Okay.
London dispersion forces are what keep materials together, unless they're held together by ionic or metallic bonds. And there's no metallic bonds between, say, two glass slides, or even between two independent pieces of metal necessarily when you sandwich them together, because you're not combining the material in between. You're just simply putting them next to each other.
Okay, that is definitely something I need to look into, and I'll admit that fully. Yeah, because I was on the concept that it was purely 100% air pressure acting on all sides, and it seemed logical for me, so I went down that route. But I will look into that. As far as this is concerned, on the total thing, yeah, sorry, to get back to your book, it was just that how I was presenting it is that by dropping the book, you've removed the actual air going, or this 1 ton of air, some of it, obviously, not all of it, applying on the bottom of the book. The book is taking all of that air pressure, basically. So the actual tissue is naturally going to stick to it, because the tissue should essentially have more of a force acting on it from above than below.
Well, here's the thing, though. The difference in air pressure between the top and the bottom between these two surfaces is negligible. It's basically zero. So if I have a tissue paper, like this is a side-on view.
It's less than that. It's five points, isn't it? 0.001 to 5.
So the difference in the forces being applied by air pressure on either side is basically zero. But all the same, it's going to accelerate downwards at some rate, and it's nowhere close to being zero. We can actually observe a tissue paper falling down. Now, the thing, though, is that I can, say, for example, crumple up that tissue paper, reducing its cross-sectional area, which reduces the force of drag, and observe as this thing falls down even faster. And what we will notice is that as we decrease the force of drag, so in other words, if I was to say the net force is equal to some downwards acting force, which I'll just call FD for now, plus force of drag, which I'll go with capital D. Here's what I'm going to do. What is the net force as I take the limit as the drag force goes to zero? So that is going to be equal to basically FD plus the limit as FD, like F capital D, goes to 0 of F.
Yep.
Now we can just do direct substitution. This is equal to just FD plus 0, which is equal to FD. And what is this downwards acting force? We can quantify that. We know what it is. It's gravity. I can test it empirically and determine its properties. You understand that?
I understand that from a yes. That would be the same situation. Put it this way: the observation would be identical on a flat Earth. It's just the conceptual understanding of what is causing that is the difference.
Okay. Here, let me just put this very simply, okay? Can you tell me an expression using that doesn't involve gravity for a downwards acting force?
It is what is measured. So it is 9.8 meters per second.
Here's the thing about understanding physics. I need to be able to come up with a description that's what's called predictive powers. That's one of the main criteria for a theory. I need to be able to say, this is how it works. I can predict how it's going to work in the future. And then when I go to test it, I can confirm it. I can use Fg is equal to, the magnitude of Fg, that is equal to some constant, which I'll call g, times the mass of one object times the mass of the other object,
Sure.
divided by r squared. I can empirically verify this. I can first take two objects, measure their masses, determine the distances between them, figure out what that force of gravity should be, and then go and empirically verify it, and it will match what the description says. And so if you're going to tell me that this doesn't work, well, first of all,
No.
it does. That's the main problem.
No,
and so
that's
do you
what
know
I'm not
how
saying.
to even replace a theory?
No, that's what I'm not saying. I'm saying that G, I mean, that it's a basic inverse square law from there on between two objects, but that G, it's the concept of the cause of that G, which is the question.
Okay.
Not
as far as
not
we can
not
tell,
the mathematics.
the reason that gravity exists is because it's just an intrinsic property of matter, just as an opposite set of electric poles will attract each other, like poles will repel.
Sure.
Quarks are attracted to each other in the nucleus by the strong nuclear force, and then the weak nuclear force causes beta decay. That's just an intrinsic property of matter.
Sure. But what I can say, and it leads me beautifully onto the next bit, is there are exceptions to the rule.
Sure.
And I don't know whether you saw the 3 examples I put there.
I did, and you're a little off base, but just bring them up here so everyone can hear them.
Can I share my screen?
Yeah, you can share your screen. I'll stop sharing mine so I can see yours.
Okay, let me even. This document was too large. I shouldn't have bothered. I should just put bullet points. Give me 2 seconds. I feel like Rumpus. If anyone knows, there we go. Him and his refraction document.
You're feeling your rumpus?
No.
So
if anybody knows,
that's weird.
If anybody knows who Rumpus is, he's been working for about 1.5 years on a document, and it's about 600 pages, and it auto saves, and it crashes his computer out every time. It's funny. Either way, so we have MC Toon.
Yes.
These are not my videos, okay? So I'm not going to show the videos.
Okay.
I'm going to explain them and show you a screenshot so everyone can go away and actually look at these. So if I just that's the link to the Hangout. So first one is, and people have seen this guy as a crackpot. And in all honesty, I don't believe in aliens, and he on his deathbed was supposed to have said aliens existed. But Boyd Bushman, he was actually somebody who worked at Lockheed Skunk Works, and his interest was anti-magnetic energy. So what he's explaining here is
it doesn't make any sense.
Well, what it is just to explain it, and you'll understand its resistance. What he done is a series of drop tests. He'd created 2 rocks of equal mass, so they weigh exactly the same, but one of them had its innards dug out and 2 massive neodymium magnets bolted together with their opposing fields going towards each other as much as he could get them closer together. And he measured the field with a Gauss meter to be about 1 meter wide. and he was dropping both of them from 50 meters, whatever, not in a vacuum, in open air, and 100% of the time, the one with the magnet in fell last.
Oh, fuck me.
Go on.
Did
So
you
it's resistance.
did you spill something?
I just spilled my beer.
Uh-oh.
Do we want to take a
Fuck's
break?
sakes. That would be helpful.
Okay. Hold on. Let's. I will.
See if you can see there. He dropped them all, and he got
All right,
several witnesses.
Hold
or
on.
many
Hold on,
witnesses.
Gleem.
Yeah.
We.
Should we have recess?
Yeah, we need recess here. We need. So let's see. I pinned you. I'm gonna.
Shall I do a rap? No, I'm joking. You ain't getting that.
No.
No, we're not subjecting ourselves to that culture.
Yeah. Gleem. Last time you were on, I had just finished doing the floor in this room here, and I had a piece of wood, and that's what. Remember, I had. I'm the worst rapper, and I had wrapped that piece of wood in some wrapping paper, and
It was a good comeback.
yeah. Well, so last week I actually did another room, did hardwood in another room. I was gonna maybe wrap another thing for you, but didn't get to it.
Yeah, I wouldn't bother. I think there's a lot more going on in the world to worry about.
Yeah. Okay, so somebody's asking what channel was Austin's debate on. So Austin debated twice on my channel. The second one he did on he streamed on his channel as well. So if you look back a couple weeks here, Wisconsin Sirens, you can find Austin Whitsitt on my channel. Now I saw just a brief part of Austin yesterday with somebody named Kosho, and they were debating, and it was the same thing. Austin makes an assertion, has no evidence, and then just insists that it's accurate, and then repeats.
Austin's a cunt. Don't engage cunts.
Tell us how you really think.
What's that?
Tell us how you really think.
He's a cunt. That's how I really think.
Oh.
No, I wanted to start a debate with him because it looked like fun, and then the more I got into it, it seemed like less fun and more like brain damage.
Yep, brain damage is good.
I can give you some of that though.
One of his preconditions for me debating was I had to tell him that he won the debate between himself and Michael. Like, this guy has such a massive superiority complex. And if you don't satisfy it, he won't let you on. Or he won't engage you.
Yeah. Kosho is the underling of Zanuck, and Zanuck is the guy that got caught asking middle school physics students for answers. Wow.
No, what I find hilarious is that he told me that Austin has a very good grasp of physics. And Austin said this himself, and I asked him, how do you have a solid grasp of physics? He goes, well, I'm on the fucking board with an engineer and a doctor. And I'm like, what does that have to do with it? He goes, well, they're very qualified people.
Yeah, the engineer that he's speaking of, I believe, is Bob Noodle. Super Noodle Doodle.
Is he an actual engineer?
He says he is. He also said that he was a multi-engine pilot, but looking his name up in the FAA system shows that he's a single-engine pilot and has not been certified since the 70s. So once Wolfie6020 identified that problem, the website changed that was hosting the FEIC or FE Core, one or the other, changed the description to not say that he was a multi-engine pilot anymore. But the Wayback Machine has a copy of it.
Hey.
So I brought a copy of it to FEIC. I was going to try to get him to sign it. I don't know if he was going to.
Love the Wayback Machine, though. Shout out to the Wayback Machine.
Yes.
Just silently working away, nicking all your work.
Yeah. So we have a question from B-Ball for Life. He says,
my ex.
Your ex?
I've got plenty of salty exes in that chat room.
Oh,
right now.
yes,
I'm not
yes.
even looking at it.
Yeah. I find it's sometimes quite distracting to look at the chat during a debate. So, B-Ball for Life says, Gleem, how far away is Polaris from Earth?
Unknown.
Unknown. There you go. All right, how's your beer spill there, Jack?
I'll survive. I think I'm good.
Did it drop at 9.8 meters per second, though? Is
Oh.
the ultimate question on everyone's lips.
Yes, it did.
The mic drop there.
You know, I had this beer because I was afraid that Gleem would be like Eric, and if Eric, an Eric-like person comes back on, I need to get drunk for this because there's no way I can go through it sober without smashing my head in.
We could switch this. I just need to prolong it out and babble a bit more so he gets more and more drunk. Nah, I'm joking.
No,
Anyway.
I'm gonna have a fucking drinking game with this.
Yeah, definitely. You can have one in a minute when every time I say ether, probably would be a good shot.
If I want to die every single time you get something wrong about physics, I'm gonna take a shot.
Sure. But what I love about you, Jack, right, is that straight up you will tell me and teach me. I've got so many people in that chat room right now who haven't got a clue themselves, but yet they will go, "You're wrong. You're just wrong," and I'll go, "How?" And they'll, "You're just wrong. You idiot. You're wrong."
Yeah.
And I never learn anything. So either way, I will say there is exceptions to that rule. Barney Tearspell, salute, shout out to him. Had good conversations with him about physics, about relativity and whatnot. But we'll get into that. Let's pick up where we left off.
Sure.
So I've got 3 exceptions to the rule, and it's not actually exceptions to the rule. It's a resistance which is normally not accounted for. Let's say this first one with the Boyd Bushman. I just found it here. He dug out someone's replicated it, or many people have replicated. Some have managed to replicate the actual results. Some have not, but they've used different specs, as in a lower height and different magnets and stuff, because they are sort of like 3-5 grand magnets or something like that. I don't know, but basically he done this. This is actually his video in Lockheed, recording the drops. So he's doing the drops, and all he's doing is just counting how many, probability-wise, it is the magnetized one falling after the actual non-magnetized one, or the standard rock. And he found that 100% of the time that was true. And that obviously, I mean, a natural explanation is there is a field, i.e. either the electrostatic field of Earth or magnetic field of Earth, which is providing a resistance, or could be the objects around it, like the brickwork, with their field, let's say, having influence on that magnetic field. Just like, you know, when you put the magnet through a copper pipe, yeah, and it creates that field that locks it in and slows it down. Similar to that. So that's one exception to the rule. I'm going to say the alternative view on all of these, and chip in if you disagree with that explanation. That sorry.
Go with the explanation for why this works.
Yep. Okay. Yep. So then there was ZARM. I don't know whether you're aware of ZARM. I think it's University of Bremen. Bearing in mind, this is a massive drop tower that they drop stuff in a vacuum, albeit what you're seeing there, as in the separate tubes there, are not in a vacuum state. Okay, and what happens is they do many drops. It's used for NASA and whatnot. It's a very, very well-known one. And what they found is when they got equal amounts of mass of metals, obviously lithium, beryllium, whatever they all are, lead, carbon, and whatnot. You had 3 exceptions to the rule in the way they drop, and oddly enough, being the side ones here. And
why are they falling upwards?
They're not. The whole thing, if you can imagine, the camera's on it, and the whole thing is in a capsule. Okay. So you put a camera in it, and inside there is not a vacuum. Yep. So then they winch it all the way up, and then they just drop it in free fall. It takes a couple of hours to suck out all the air, but the actual pod that it's in is in free fall. So they're testing things in free fall, but under air conditions as well. So this I would assume would be equal air pressure throughout. However, when dropped, something could have happened. I don't know how sealed it is. in as much as, is the air sealed in there and then it's Loctite sealed? I would assume so, because then it'd escape into the vacuum on the outside. But as I say, the exception to the rule is that all the masses were dropped. That's right at the end when it smashes down. And lithium, carbon, and lead all fell at the different rate of 9.8 meters per second for some reason. Now, I can picture or logically explain the alternative in as much as, now bear with me this, and you're probably going to have to take a shot after me saying this, but the ones on the outside are going to be the ones nearest to, let's say, even though there's no friction of air in the vacuum, there's going to be some sort of movement of that pod dropping in a vacuum. Okay. Now, if there is any external effect, i.e., the tube of the vacuum that it's in, the reaction between the two, this could have an effect in as much as it's dragging it up, similar to what I was talking about with the magnetic forces. Yeah, it can create.
I just looked at the continuous video. Do you know what this actually is? Or how this experiment is set up?
This experiment was a one-off, as I understand, by the guy who was attempting to disprove Einstein and the exact thing. And
Okay, I understand how they do this, though. Do you know why this works?
I don't understand why they're not dropping at the same rate.
Okay, here, want me to explain to you?
Yes, of course. Can I stop sharing and you take over?
Yeah, sure. I'll start sharing.
Yeah.
Okay. If I can figure out how to fucking do this again. Window. Okay, you guys can see my screen, right?
Just coming in. Yep.
Okay, so what they've done here is they've taken like let's say a small box. It could be a cylinder for all I care. And what they've done is they've got multiple tubes, let's say, inside. This is a terrible drawing, but you know what I mean. It's not to scale.
Yeah. Cool.
Ugh. They've got multiple objects inside, and what they've done is they basically, if this is the ground, they've lifted it at some height, and then what they're going to do is just going to drop this whole thing and let it fall. And the idea is that this entire thing is in free fall, and so what's going to happen is, because the air inside is not basically, if you were to drop this thing without the enclosed box, what you're going to have is little tubes that are going to encounter air resistance. This eliminates that air resistance. In other words, these objects inside here, they're not subjected to the air that's coming up beneath them. And so what they're going to do is they're going to drop this and see how these objects interact. Now, because all of these objects are more or less accelerating at the same rate, they should remain at the bottom. However, a small, tiny disturbance in a system is going to cause things to just ever so slightly move up, which is why it's completely uneven. And the reason things to crash about, like if you were to play the full video, when it hits the ground, you're going to notice that all these objects, they just suddenly bounce up and they act erratically.
That's it.
And so here's what you have to keep in mind. If we were to use this as our frame of reference, in other words, use this as our stationary frame of reference.
Sure.
We're going to use the frame of reference of the box. In a perfectly ideal system, they're all going to be accelerating at the same rate. And so in other words, the velocity v of any object, or any mass, let's say, relative to their tube, that is going to be 0. So in a perfectly ideal system, they should all remain perfectly still on the bottom of the thing until they hit the ground. Of course, you can't have a perfectly ideal system. So in other words, if you actually go back to my last debate and watch me drop the textbook, what happened was, here's my textbook, and here's a little tissue paper. Because it wasn't perfectly flat on it, as the textbook moved down, air rushed towards the side of it.
Yep, that's it.
That's going to lift the tips of this. So in other words, it actually almost separated from the book as it hit the bottom because this isn't a perfectly ideal system. That's the exact same thing that's happening here. This isn't an example of things accelerating at the different rates. The entire apparatus is moving down at the same rate, which is going to be given by the force of gravity and drag. However, the reason why things inside the system will move at different rates is because of a little nudge that occurred at the very exact moment that you drop this thing. And so, in other words, if the velocity of these things relative to each other as it's falling is zero, or rather the change in velocity is going to be zero. So what we can say is that if vi is the velocity of the object, v of crying out loud, really, of any mass right after it's dropped, vf is the velocity of any mass. And when I say mass, I'm referring to these little objects here.
I understand. It's kind of like you're saying that it's the difference between Einstein's elevator, where you're a person and you're the one object in the one elevator, the equivalence principle,
this
basically.
is a different thing entirely. So,
oh, okay, go on. Sorry.
Sorry. Any mass, right before impact. Now, because the acceleration of the entire velocity or the entire system is the same,
right?
Then change in velocity is going to be zero. And so, in other words, the displacement within the system of any individual object is going to be given by the time that the thing spends falling, and it's vi, its initial velocity. That might not necessarily be zero in a non-ideal system, because if you nudge it ever so slightly as you drop it, then you're going to give a tiny vi to every single different object, and it might shift based on how the thing, let's say, rotates. If you're holding it by its hinge and you drop it, it might turn just a little bit.
Sure. No, I understand that.
Yeah. And so then,
just a
because the
tiny
change in velocity is zero, after that, that velocity is going to carry throughout the entire duration of that fall, and thus you have objects ending up different places right before impact. So that's not an exception to gravity. That's just an exception of experimental error.
Sure.
You would
I mean,
with a more accurate apparatus, basically.
Yeah. I mean, I will say the guy actually wrote a paper on this the guy who designed it. He actually was met with resistance first off because he wasn't backed, put it this way, but then he got financially backed for it. They allowed him to do this one experiment. He then writ up a paper challenging Einstein's relativity because of this, and was suggesting and then reapplied back to them with the backing again to do it in a vacuum state. So the internals are in a vacuum state as well, and they politely declined. Whether that was because of him writing that paper, but he was immediately slated, obviously, by the mass community for writing that paper, and he admits it. He goes, "I know, I'm going against everything, but this is what I've done."
It's not just someone that he's going against everything; is that the experimental process is just a bad setup. It would be like me, have you ever heard of a guy named Andrew Wakefield?
No, I don't think I have. No.
He's the guy that more or less started the anti-vaxxer movement. So what he did was he took a bunch of random samples.
Yes, Wakefield. Of course, he's from over here.
Aluminum or something rather in their brain samples, and he said, therefore, because aluminum damages the brain and aluminum is contained in the vaccines, therefore this causes autism because all these brain samples are from people that have been given vaccinations. He didn't have what's called a control. So in other words, he didn't compare a healthy human brain sample with that of a non-healthy human brain sample within the same population group. And so he could have very easily verified that they both had the same level of aluminum in their brain samples, because aluminum is ingested with things like eating fish or if you're eating contaminated foods. The amount of mercury or aluminum you get from a vaccine shot is absolutely minuscule. And so when people replicated his test, they of course found his results to be faulty because he had an improper experimental setup. That's the exact same thing happening here.
I think, just to be clear, it is mercury, not aluminum, that is the concern.
Well, mercury is another thing too. People assume that it's some highly toxic material that's gonna kill you. It's not methyl mercury. It's not a compound that's highly reactive. It's a less reactive compound. And the reason we have that mercury-based compound in a vaccine, and I know I'm getting a little off topic, I just might as well explain it now, is because you don't want to give someone a shot that could have bacteria or viruses in it that you don't want there to be. So in other words, you can't inject someone with a shot that's not sterile. If you do that, you're going to give someone blood poisoning. That's why you have a little bit of a toxic material in there just to sterilize the whole thing. But it should be minuscule enough that it won't affect you. But people simply misrepresented the data and said, therefore, there's a correlation between mercury and vaccines and autism, and it spun off from there. Even though anyone with any credibility in the field of science evaluate it and say, hey, this process is absolutely messed up. You can't derive anything accurately from that.
You see, that explains it much better than the dark web explains it. In these dark web circles, you see, they explain it where they see it as a ritual in dedication for Newton, because he used to. Joking. Anyway, are we halfway through? Because the exceptions to the rule, there was a final one, which again you're gonna say exactly identical. Just let me share my screen again, if that's okay.
Sure.
You're gonna say exactly identical that it's a bad setup. However, the guy who actually designed this kit, he actually made this dual vacuum, a side-by-side vacuum, where he's doing it. He's a University of Washington physics lecturer, and he's doing it just because there was nothing on the market that was precise enough. So he takes you through how he built it from scratch, and it is very simple and very, very basic, let's say, but it's a simple demonstration apparatus to show two separate vacuums side by side, and you can put a different object in each. Now, by watching it normally, what he does is he drops a coin and a guinea coin and a feather, a yellow feather in. And how it works is he's turning it around. It's a one-piece unit. So if you look in the side on, it's like a one-axis.
Okay, I know what you mean. Yeah,
yep, exactly. Exactly that. And I don't want to get you a strike, even though he's not. I don't even think he's a lecturer anymore. But he designed this, and looking at it at normal speed, it looks like they do land. And obviously, for his general purposes, it shows what he wants to show, that both things fall at the same. But when you actually slow it down and take it frame by frame, you actually see them both falling. Like if you can see there, that's flat already. I mean, there is a couple of bounces, which I shouldn't actually blag on, but it doesn't fall at the same rate on every different drop. Now, obviously, I can then counter that with myself and say that could be hitting the side. It could be how it's dropped. And as it's spinning, there could be a disequilibrium there. But obviously, he's a physics lecturer, so he's designed it to a certain degree of accuracy, which is fit for purpose, obviously, to show exactly his students.
Experimentals out. I want you to understand this is just a demonstration apparatus. You're not going to use it to measure anything remotely close to what you want for a paper.
Sure. No, I do understand that, but what I'm trying to get at here is that there is exceptions to the rule, and your answer to that will be yes, of course, when there is alternative forces or resistance to the system. But now, finally, I just want to spend 5-10 minutes on saying there are two major other issues I have. And MC2 may want to chip in here, but because he actually read Vera Rubin's paper, I think. But there's two other issues here that gravity does not work as expected, let's say. And that is in the galaxy rotation curve at a massive scale, and at a very small scale, it's actually completely omitted from the standard model because it used quantum field theory, and it's incompatible with general relativity. So I would love to say, so yeah, you've got a concept of gravity, whichever, and I don't mind whichever. I'm not one of these pedantic ones that says, oh, Newton's is a force and Einstein's isn't a force, albeit Einstein's is the correct understanding today in current physics, as I'm aware, but you can use Newton's as an approximation, let's say, and it works to a very good distance in the solar system mainly. But obviously, there are massive exceptions to the rule, and I will say massive because dark matter and dark energy, basically saying that 95% of the cosmological model is supernatural.
That's not what it says at all. Supernatural means we can't describe it using physics. The whole point of us hypothesizing dark matter and dark energy is that we can describe it using physics, and dark matter is very it's not as erroneous as most people make it out to be.
Okay, I mean, there are many papers that say it don't even exist and it could be resolved mathematically. I mean,
Yeah, but
that's
none
the
of them
same
have
for
been
dark
backed,
matter.
though. That's the thing.
Yeah, I mean, some have entered the actual peer review. I mean, Eric Verlin's Entropic Gravity, that basically says that gravity is not even a fundamental force. It's a
Yes, but
byproduct of.
even if it passes peer review, it's just a preliminary paper. You need to be
Yeah,
able
no,
to
only
submit
past
a
first
first.
stage. Yeah, only past first stage. It failed because it's a Mond-based solution, and it didn't. Put it this way: it resolved dark matter, but it didn't. It required dark energy to do so. And the
How about I just
result.
explain what it is you're saying in very simple terms for everyone, so that we all
Sure,
know what.
sure,
Okay.
definitely. Yeah. Do you want me to stop sharing?
Yeah.
Yeah. There we go.
Ah, come on, come here. Window. Okay. So when we say we've replaced Newtonian gravity with relativistic theory, there needs to be a very clear distinction here. So when we say, oh God, you guys can see my screen, right?
Yeah.
So a theory, let's just cover this very simple. It describes some physical phenomenon. It describes phenomenon. It's going to have first principles, which we call axioms.
Yeah.
And then from these axioms, we can derive properties.
Okay, I'm with you. Yep.
Okay. Now, every theory has a set of things that it can accurately describe. All right. So, for example, let's say this bar represents the things that we can accurately describe using Newtonian mechanics. So we'll call this NM for Newtonian mechanics. Now, if we were to extend this a little more, these are things that we cannot describe accurately with Newtonian mechanics, but we can describe accurately with relativistic mechanics. And so what this is the set of all things that we can describe accurately with general relativity. And so in other words, this set of all things that we can accurately describe using GR is going to be what we call a proper superset of the set of all things that we can describe using Newtonian mechanics.
Sure.
So what this is saying is that everything that we can accurately describe here, sorry, I keep lifting my thing by accident. Everything that we can describe here, we can also describe here. But there are things that we can describe in this section that are not described in this section.
Yes.
So
I
that's
get
where
that.
we are right now. So in other words, when we discovered that the orbit of Mercury precessed, that wasn't showing that Newtonian mechanics was broken. In order to disprove a theory, what we need to do is show that this doesn't actually exist. It cannot actually make accurate predictions.
Sure.
That was not shown with Mercury's orbit. All that showed was there was something that the theory did not describe well. And so all it showed was that our theory was incomplete, and we improved upon it with general relativity. Now let's just go into GR just a little bit here. So the simplified version of Einstein's field equations is this.
Yep.
And I'll just explain what these are. So this is called the Einstein tensor.
Yep.
This lambda is the cosmological constant.
Sure. Yep.
And this is the metric tensor. This is just a constant, a pi, and this is the stress energy momentum tensor. Basically, this represents mass and energy of a system. And basically, we can just say this is the matter of a system.
Yep.
Matter. And this represents space-time. Now, there's two problems that we get that you've touched on. One is on galactic scales, and one's on quantum scales. Let's tackle the quantum one first. In order to describe a gravitational system using quantum objects, the part of the equation that defines the matter has to be able to be defined in quantum terms. Yes, that makes sense?
Yeah, definitely.
And we can actually build a stress energy momentum tensor that's in quantized terms.
Sure.
The problem is we need to figure out a way to quantize this bit.
Yes.
Now, what do we mean by quantize? We mean that things can only exist in discrete states. So, for example, the energy state of an electron in a hydrogen atom can exist in energy state 1, 2, 3, or 4. Basically, E is equal to some level n times the ground energy, E naught. And we define n as just some element of the set of natural numbers.
It's the orbit.
So in other words, it can exist as 1.5, 2.3, square root of 3, and so on and so forth. The thing about space and time is we don't see that and in a way that makes sense. We can't say that time only exists as 1 second, 2 second, 3 second without anything occurring in between, and we can't say the same thing for distance either. And so that's where we conceptually have a problem with general theory of relativity. Now we do have a way of sort of getting around this, and this is basically the lead method so far. We're going to use what's called Jesus Christ. We're going to use what's called the expectation value of the stress energy momentum tensor. Do I remember my bracket notation? GUV. That's probably bad notation, but whatever. It gets the point across. This is what we're saying is what we expect this value to be in most occurrences using basic statistics and quantum mechanics. This is what we call semi-relativistic gravity, where we have relativistic or classical relativity, if you will, on the left-hand side, and sort of quantum on the other. The problem is that this is basically not a formal description that carries you very far. It still does not get rid of things like singularities in black holes, or at the very beginning of time, if we were to go by the CDM model of cosmology. And so this is basically our best fit so far, but this is basically the conceptual problem with trying to create a quantum theory of gravity. There's two big ones to get around this. One is to basically go by completely different axioms and go with instead what's called loop quantum gravity or string theory. Both of them have basically not gotten very far thus far, but they are making some progress. Now, as far as galactic seals is concerned, this one is much simpler. So basically, if this is your galaxy, bad drawing. If that's your galaxy, what we see is that the amount of matter within, in other words, this term here, does not equal this term on the left-hand side. There's not enough mass and energy in order to give enough curvature in space-time for galaxies to remain together and not just spin themselves apart. So in other words, we are missing some mass and energy from this part in order for this all to make sense. Now, here's the interesting bit. We know where to look for this missing mass, though, because through gravitational lensing, we know that whatever matter is around, or whatever dark matter is, we know where to find it. It's going to be in sort of what's called a halo around the galaxy, because this is where we observe gravitational lensing. So we know where to look for it. We know that something there is causing this distortion. So in other words, we're almost certain that there's mass there. And we know several things about dark matter. So if we're going to list the properties, it can interact gravitationally. It does not interact electromagnetically because there's so much of it that if it could interact electromagnetically, it would emit a lot of light that we've observed before. And so there's going to be no EM. That's what we know of it so far, and that's basically what we're going off of. Now, this is a very similar thought process to how we discovered neutrinos. Basically, when we looked at, say, an atom that went through beta decay, so it emit some positron or electron. So we're going to put for positive. It would emit some photons.
Yep.
And then this would decay into another atom of lower mass and energy. The thing, though, is that if we were to try and take the energy and mass of the system initially, it does not equal the energy and mass of the system after it goes through beta decay. Because even if we were to sum the energy from what's left of the atom, what's left, or what we have in the photon, what we have in the positron or electron, we still don't get the energy that we got initially. And so what physicists said was, what if there's some amount of mass that's escaping in a particle that does not interact electromagnetically? It's very weak because we cannot detect it or thus far. But there's what we're going to call a very weak interaction between this particle, whatever it might be, and the atom initially. And this is where we made up our missing mass. Now, at first it was just a hypothesis, and then a couple of decades down the line, we in fact discovered the neutrino, which has a very tiny mass, no charge, and it interacted with what we now call the weak nuclear force. And so we're just using the same process here to figure out what the hell dark matter is. Now, dark energy refers to something entirely different.
Sure, yeah. I mean,
A
just
couple of decades ago, after Einstein published his field equations, we had a guy named Alexander Friedman. And Friedman, he derived three possible cosmological trends from Einstein's field equations. So these trends, if you will, are that the universe is, on average, on very large scales, contracting. In other words, the distance between large objects like galaxies and galaxy clusters is going to decrease. Or the universe could be relatively constant. So in other words, the distance on average between very large systems of mass is not going to change, or it can be expanding. We have empirically verified that it is this one. And so the problem is that there needs to be something that does work on these large systems. And we don't know what that is. And that's why we call it dark energy, because as we recall from what we described earlier, energy is defined as the capacity for something to cause a physical change in another object. The other object in this case, is going to be large systems of matter like galaxies and galaxy clusters. What's causing that work, that process in changing the energy between objects, we don't know. And so that's why we just call it dark energy. It's not supernatural because we can describe it using our description in physics. We just don't know what it is. That's a very weak argument to say that gravity is fallacious just because we don't have a complete theory of it. Because we even have descriptions of what the missing links are. We just don't know what they are specifically. We don't have a way to observe them directly thus far.
yeah, no, I actually think that you've done a perfect job. You see your subset one there. That was a perfect job and a perfect argument against the likes of Sleeping Warrior, who would say that they're totally separate. Einstein debunked Newton when it wasn't. It was a build upon, and you explained it perfectly. You explained that whole thing perfectly. Well, I'd like to just close off with you can possibly come back, but let's not go into any depth because we're going to run out of time for perspective.
Sure.
Yep. So to counter on the dark matter side, number one, you were basically the actual thought or the conceptual thought is that we need to invoke some sort of matter that we haven't discovered yet. Okay,
Well, we
how
know
to?
it exists. Now, that's the thing. Because
Well,
we've
this is
observed where it exists. We know where to find it. We just don't know what it is exactly. Because it only interacts gravitationally. And if I was to say, take a handful of dark matter, because it can only interact gravitationally, which is for any given object can be much weaker than any of the other fundamental interactions, with the exception of the weak nuclear force. Because it's so weak, it's very hard to basically measure its properties. But we know it exists and we know where to find it.
Well, this is a point of contention, I think, and you would probably know better. So I'm looking to you for I mean, you've done an amazing job. I will say salute for that. But stop dropping stuff because that's just trying to prove gravity. Again, you're doing the same thing. No, I'm joking. But what I can say is, if I've seen papers that obviously there are proposals being put forward, and science isn't going. No, we're not going to dismiss that proposal. And the proposal being is the likes of Eric Verlind, number one, saying that gravity doesn't actually exist as a fundamental force, even though, again, it hasn't actually got through to any stage of peer review completeness. It's only been accepted into it, let's say. But he is working on it. And I'm sure you're aware of the full concept of that, where he started from the building blocks of quantum and worked on the background quantum foam field, and then calculated that up, extrapolated, and managed to resolve dark matter just by those calculations. Now, there are other theories which rid dark matter as well, multiple being put forward. I'm not saying they're accepted or peer reviewed or anything like that, but I'm saying there is contention for exactly what you're saying, that people are starting to doubt it, because if you think it was found back in 1930 with the likes of Jan Ort and Fritz Zwicky, then obviously Vera Rubin done a work 1950s to 1980s, and it's one of the oldest outstanding problems of physics. So they are looking for. I mean, there's been massive failures of projects trying to look for it on Earth, with the ice lab down in Antarctica, and they've not found a thing. And obviously it's difficult. It's a very difficult thing. But to say that there is definitely some sort of matter there that we don't know about, to me sounds supernatural straight away. But I don't think you can definitively say that when there are other valid physicians, so say, or people in physics that are putting forward theories that contradict that statement.
The thing about their descriptions is they need to first be able to describe everything that we have in GR and Newtonian mechanics, expand upon it, and also they're going to need to account for that mass that we know exists because we've observed gravitational lensing from something that exists around large galaxies. We can even observe these collections of erroneous mass in the cosmological background radiation. So we know that it's somewhere there. We just don't know what it is. That's the main thing. If you're going to try and replace it with some other theory, you're going to need people to explain that. And thus far, that's why they failed.
Okay, I mean, I will say there is one thing, and I cannot say this, and please don't say I'm putting this forward as evidence and direct proof or anything like that. But there's a guy called Stephen Rycroft. I don't know whether you've heard of that name, Dr. Rycroft from CERN. He invented the bubble chamber analysis. He was the first guy to done that. He done a, so to say, let me hold up my fingers without you seeing me, a toy around paper with dark matter and trying to resolve it using electrostatic potential differentials between the inner and outer. And he actually managed to make, at the end of it, he says, caveat, I am not submitting this to any paper at all, and I am not doing this to promote the electric universe theory or anything like that. I was just toying around with the idea, and he could equate the two, let's say. So disappear, make dark matter disappear with just the electrostatic differential of it holding the matter in, let's say. So there's exceptions to the rule, again, which can be explainable, because obviously we're going into a whole new realm of gravity when we're talking electrostatics. So
Yeah.
I think we should move on to perspective.
Go to perspective.
All right, before we do that,
Okay.
I've got a couple questions here. Punchy says, serious question for Gleem. What's the best way to make a BLT?
I'm veggie.
Oh, no. Gleem, I'm sorry.
Oh,
I mean, Punchy, I'm sorry.
kick them off the stream now. Ugh.
21 years.
So, all right. And speaking of Punchy, now, Punchy was here last week. We were going to go to a concert, which got canceled because of this virus. So he brought me some of these here, these ketchup potato chips, which I'm going to eat. I got chopsticks because, you can't be too safe. So,
As you do.
yeah. Who doesn't eat potato chips with chopsticks?
I'm Asian, even I don't do that.
There we go. I try to eat pizza with chopsticks.
Ah, yeah.
Yep. I do not like them, Sam. I do not like ketchup potato chips.
All right, let's get back on topic here.
All right.
Yeah. Straight. We'll make this one shorter than gravity, because you did do a thorough explanation there, and there's a couple of things I do need to look into. Yeah. And you did explain it good. I've got the reservations on the very fringes of that lack of understanding of science, let's say, but let's roll with the perspective side of things.
All right.
So you're obviously aware that there is this the battle between both flat earthers and globe earthers is what is blocking stuff at the horizon. And
Right.
flat earthers point of view is there's multiple things, and the two things are basically perspective and refraction. Some have renamed that to ether band. Take a drink if you wish, but it's essentially that. It's the combination of your perspective and refraction or blockage, and I'll get to that later. But do you agree with that statement, that is a core thing or a core argument between the two? And would you agree with the statement, you cannot hide anything bottom up using just perspective?
Perspective is a vague term. You're going to be way more specific than that.
Okay, let me try and share a screen. I'm gonna start off with an optometry paper. Now bear in mind, I won't follow the document because it'll make it so much longer. Okay, so we'll just jump straight to halfway through. Let me share my screen. Here we go. So what this is back in the 1950s, there was an optometrist who decided to um, figure out distance judgment. Okay, so she wanted to basically see whether the size distance relationship, which is in a nutshell the um, angular resolution or the angular diameter formula, um, and what she was doing is playing, not playing, but experimenting. I mean, there's multiple experiments that she did using people, test subjects, obviously all human eye based. So this is merely mind perception to distance. Basically,
Okay.
that's how she's doing it. And as I say, is there a discrepancy to the general rule of your standard angular diameter formula of it proportionally equally reducing in size? And she found that there was an error. Humans did have an error, and it, it got worse at height and at distance. And what she went through, I don't know whether you can see that properly on there. Um, this this basic equation, which is distance equals the height of the tangent of the angle. So it's from there to from below horizon to eye level, and she's just basically put in objects, let's say 10 meters, 20 meters, 30 meters, 40 meters, and whatnot, um, without another reference object, which is very important. Okay, so the observer is trying to guess how far it is away without knowing. So they're putting it at random places, and they're finding that there is a consistent, no matter how many times they try it, humans have a consistent brain error. So much so that in 1986 or something, the U.S. Army had to change their grenade sights to account for this exact. Basically, the grenaders were firing short all the time, and they were just wasting rounds in practice, and they were wondering why. And it was because of this shortfall in perceived distance. Okay, so obviously this does not relate to a camera, but what I see a lot of the time is in the globe earth analysis showing that perspective cannot hide anything, because you can agree here, looking at something in an orthographic view.
Uh-huh.
Yeah, if you had a direct line to an object, let's say the object is the same height as the person, um, there is nothing blocking them at all. You could have this line infinite, or not infinite, but let's say hundreds of kilometers, and there would never be, these two lines would lay parallel. Your eye level and the floor would always be parallel. They would never converge, and nothing would be blocked. Obviously, you should be able to see that object. However, once you take a perspective view of how we actually view reality, you do get a limitation. And what happens is, obviously, your floor appears to rise to eye level, and from my point of view, you can only see a limited amount of the floor. Okay. Do you agree with that statement? Because I need to, as a human being, whether globe or flat, due to your perspective around you, you will only see a limited amount of the floor anyway, because you will not be able to resolve something at a certain distance, or the floor.
You can only see part of the ground. If you have an infinite plane, you can only see part of it with any level of acuity. But sure, I mean, you could still technically see off to an infinite distance. It would just be so the angular diameter of any object at that distance would be so small that you wouldn't be able to resolve it.
Exactly.
So,
Yeah,
fun,
no,
but,
that is exactly it. So
yeah.
in my eyes, the way how I like to explain it is that you stand on a train tracks, the old train tracks that are merging off into the distance. You see 100 rungs of the train tracks going up. They're all at equal distance, let's say. Then you lay down on the train track and reduce your height basically being the core thing, and you only see 10 of those. And what is actually happening is the beyond 90 are getting compressed or hidden by the foreground, if that makes sense.
Sure, but you have a problem with your analogy in ships going over the horizon or anything being obscured by the curve.
Okay, well, either way, we'll get to that. We'll get to that. But it is, I don't see the problem with there being a limit of the floor that you can see before that. What I like to call it is a false horizon. You're creating a false horizon. The actual horizon of a globe on these train tracks are not 10 rungs away. It's just that your however far you can see miles in the distance is compressed into that 1 pixel line, which is known as your horizon.
Mhm.
Yeah. And obviously massive objects behind that, like a train coming up, in my eyes, a train coming up, if that was at the 100th rung, you would not be able to see the wheels because they would be blocked by your foreground distance if you're laying down on the track. I don't know whether I'm ready to commit suicide at this point, but I'm laid down on the track and I can only see 10 rungs, but I can see a train in the distance. However, its wheels are blocked. Okay, that's how I'm seeing it. And it's because of that acute angle. You haven't got enough of an angle to resolve it. If you stood up again straight away, you can see that. You can resolve that because it opens up and you can actually see it. So please counter that. What is wrong with saying a false horizon is incorrect?
Sure, I'll present.
Can I stop sharing? Because that is hopefully I've explained it on behalf of flat earthers very well, because that, I think Nathan Oakley even put out a video just today explaining something identical along those lines. So you'd be countering that video as well. And I'm not associating myself with Nathan, but I do salute him either way.
Okay, so so you're standing here and you have, let's say, just some, because this is the classic examples. Let's just say you have a ship, okay?
Yep.
Now, if you have to look at, because let's say you're on a beach and so you have like waves or whatever, and you want to look at the bottom of the ship. In other words, you're looking downwards. What you say is true. You're not going to be able to resolve things between like waves and the bottom of the ship after some distance because of the limited acuity of your eye. The problem that lies, though, is that, well, okay, I'm going to draw this better to scale. Or a better representation, let's say. Is that not everything is going to be you're not going to be looking down upon. If you have to look up, there's nothing that's going to obscure it as it moves further away. And actually, if you think about it, if I were to draw another flat plane here, and you are sitting here, and let's say you just have a bunch of poles around here. A bunch of poles that are taller than you that go off into infinity, okay?
Yep.
I'll just draw this better. So you have to look up at every single one, correct?
Sure.
Because even at infinity, basically, if you want to solve for whatever this angle is, this upward angle, we'll call that alpha. Alpha, we can say, what trigonometric ratio do I feel like using? Let's use tan. So tan of alpha is going to be equal to the height of the pole, which we'll call h, minus your height, which we'll call little h. So it's going to be equal to h minus h divided by the distance d. And so we can just easily solve for this angle alpha with using the tan inverse. So arctan of h minus little h over d is going to give us that angle alpha. And if we take the limit as d approaches infinity, it's going to equal the limit as d approaches infinity on the right-hand side as well, of arctan of h minus little h over d. And so what we're going to get is, if we do evaluate this as d goes to infinity, As d gets infinitely large, this entire thing is going to go to 0. And so we can evaluate this simply as what's arctan of 0, which is equal to 0. Now notice how this is still not negative. So in other words, what we can say is that alpha is always greater than or equal to 0. It's never negative. But if we were to try this experiment in real life, what you're going to find is, and here's basically a much more accurate for doing this. Michael, you can correct me if I'm wrong. What's the tool called for measuring elevation angles? A theodolite?
Yeah, theodolite.
Yeah. So if you were to do this, or actually if you were to remove the human perspective entirely and just use, say, a laser rangefinder or a radar device, a future crosshairs, and this is your ship initially, what you're going to find is that eventually your ship is going to be at a lower elevation. So let's say you pick this as your reference point. At some point, like let's say this is the horizon, because you're looking down upon it at some elevation, like some observer height that's not 0. So if that's what you're seeing initially, what you're going to see finally is maybe just the top bit. Now, we've just established that if something is, even if it goes infinitely far away, this angle should never go below 0. But empirically, what we find is that that angle does dip below 0. It goes negative. So if we were to define, this is our y and this is our x, if we define this as positive, then for that angle to be negative, we have to be looking downwards. And that's exactly what we see empirically if we do this in real life, which should be impossible on a flat Earth, regardless of whatever perspective you're using. Because no matter how far away you get, you should never have to look down at an object that's not rising or sinking as it gets farther away.
I think I get where you're coming from there, but if I could just take over the screen again,
Sure.
let me just need to bring up something. Sorry, it takes a while to bring up as well because it's pretty big. But basically, on the from the flat earther's point of view, there is a perspective limit of based on your height and the resolution of, let's say, a camera or whatnot. A laser would be slightly different, and radio waves, I think, would be slightly different as well. All suffer from refraction anyway. But with optical limits, specifically talking optical limits, let me share my screen. Sorry. So what I've done is try to do this to scale. Obviously, you'll be aware that it's stupid. It would be stupidly big if I'd done it to perfect scale. But what I've basically done is an observer here, if you can see that. Now, I've acted as if this observer is 1 meter high. So as you can see, obviously that is completely disproportionate to this. And obviously you'll agree that if this was to scale this way, you would be 2 pixels up there and you wouldn't see the conceptual regards of how the flat earth sees it. Yep. So if you see, obviously you got the rays, let's say, let's follow the rays to each marker of 1 kilometer, 2 kilometer, and this goes up to 40 kilometers. But you see the red lines there. So the yellow lines are the markers for the kilometers. The red lines are going to be the horizon line for each individual device on how far that it can see. So for the human eye, you would get an approximate, put it this way, if you got an object that was the same height as your observer height and you took it out into the distance to a point where you cannot resolve it, that would be approximately, it's between 3.5 to 3.9 miles.
But
So
the thing was, at the top of that object will never dip beneath eye level. So it will never go to a point where your elevation angle for where you have to look to see the top of that object will be negative. But that's what we see empirically. That's mathematically impossible on a flat plane. You understand that, right?
No. This is what I'm not understanding. And if I just explain this next bit and then get up to the actual lighthouse at the other end, I think you'll understand. And what I've done is I've seen flat earthers do these diagrams, and I'll show you a couple that other people have done, but I'll show you how they're representing it. So this is your horizon line. That's the limit of how much you can see on the floor or resolve of the floor before all of this here gets compressed into a single pixel. Yeah. So if I move along now, we can see here, I've actually taken these from websites that have calculated the actual distance, the visual acuity, the angular resolution that is its maximum in reality. So you've got the P900 limit, it's about 9.5 kilometers, and then you've got P1000 limit, and this is of course without any refraction. This is just purely geometric.
Right.
But we are now at 19 kilometers, and we are at the limit of how much we can resolve of just the floor. And obviously now everything going towards the lighthouse on the opposite side up to 39 kilometers, 20 kilometers after, is all compressed into one single pixel. So if you can see there, that's where the P1000 is in the middle. That's where the horizon line would be for a P1000. You're just zooming in on this ground and you can resolve it up to this stage. But then it's this discrepancy here, this shortfall, which causes a blockage, and it's an apparent blockage rather than a physical blockage. Okay, so it's not physically blocking. It's
You're not blocking anything. You just can't resolve anything at the bottom of an object. That's not going to change the fact that the top of that lighthouse will always have to be something you have to look up towards. But again, for a tall ship, we have to look at the top of it as it goes further and further away. Eventually, you will have to look downwards in order to see the top of that ship. That's not possible on a flat Earth.
Yeah, I don't kind of get what you're saying there, because if you're watching a ship, if you're on a mountain, let's say, and you're watching a ship go over the horizon, are you literally saying that at one moment you're seeing the back end of the ship, and then as it's going over the curve, you're then seeing I don't know.
Okay, now let's
You wouldn't
just
see
go
the.
back to my screen and I'll show this to you again. Okay, I'll go
Yeah,
back.
sorry.
So let's go back to look at me here. Let's go back to this. If you have some object, let's say that this is your lighthouse, okay? And I'll just remove the math here because I don't know, maybe it's confusing or something.
Sure.
This angle alpha, you'll never be in a position where alpha will be negative. In other words, for a flat plane, an object that's taller than you, as it gets further and further away, this angle never goes beneath zero. It will always be positive. You'll never have to look down at an object. And so, in other words, on a flat Earth, what you should see is, let's say, here's our theodolite. Let's just say that this is the very top of our object. And we'll do the same thing. As it gets further and further away, as let's say it goes to infinity, what you're going to see is that object's going to drop lower and lower and lower until it finally reaches here, assuming you can still see it. That's not what happens in real life. If you do it empirically, here, I'll just redo these just so I don't have the messy attempt of drawing of a ship. Even before it gets to a point where it's so far away that you can't resolve it, what's going to happen is if you start at here, eventually that top of the ship is going to be here, which is impossible on a flat Earth because I can just visually demonstrate this. No matter how far away this is, you will never get to a point where you have to look down at an object because the height doesn't change.
Now, can I just ask you to do something then? If you let's say, got your crosshairs and they are on the horizon. So if you draw a blue line or some waves going across one of the horizon lines, yeah. So you're on that. Now, if you draw a square box, as in the back of a ship, in the crosshairs. Now, how flat earthers would see this in a perspective form is that horizon line that you're seeing there is that limit where I was just talking about. So whatever tool you've got, that gives you that how much you can resolve of the floor. Okay, now
is that what this is basically assuming is if this is your theodolite, that's your theodolite. In order for this to be true, what you would need to have this happen, what needs to be occurring is that this is basically buried in the earth, and so that their observer height is zero. What we're saying is, because if you actually have your theodolite buried in the earth, you're probably just not going to see shit. If you have it above ground and look at an object that's very far away, eventually it will get to a point where the top of it is beneath is beneath the center of the cross. In other words, you have a negative elevation angle. That's not possible on a flat Earth for an object that's not changing its height.
Right. No, this is what I'm not getting. If we go back to exactly what I was just saying there, there's one final bit to add where obviously the waves are very close to you in comparison to the ship. So as the ship is going off in the distance, it is also reducing in angular size. So it is reducing and appearing. So your waves are still there because they're sort of like your foreground blockage, your forefront, and then you have the object moving away from you, just increasing. But because the bottom of it's blocked, only the top of it is decreasing in size and going down, and that's what makes it appear to seem it's going over a curve, where it's not. It's just going out of view, and you can even say this on the likes of ships half cut off completely, half cut off, and even massive view. There are many pictures there. It's all based on your height, how much of you can resolve of the floor, and then any object beyond that, the bottom of it will be blocked by your inability to resolve the floor. Okay.
But that's dependent on the fact that your observer height is 0, and so you're looking through the dirt, basically. That's not what's going to happen in real life where you have an actual observer.
Well, I don't get how you're seeing, when you say, yeah, we can measure it below this wave, let's say. And this is what I'm saying. Visually, no, you can't, because it isn't. You can't see it. It's just gone out of view.
These are your waves, okay? Those are your waves.
Yeah.
And here's your object.
Yep.
You will never be able to block anything that's above this point, like the highest wave, using just the waves, no matter how far it is. Do you understand that?
This is my point. Yes.
Never obscure the top of the lighthouse on a flat Earth.
It will if that change angular size.
It will not, because you have to look down at these waves. In other words, you have a negative elevation angle, and for these ones, you have a positive elevation angle. They will never obscure each other. What's going to happen is, as this gets further and further away, you will always have to look up to see the top of this lighthouse, or the top of whatever object it is that's moving away. What's going to happen in the real world is, as you are trying to do your measurements.
I don't see it as that. I don't see it as that at all.
I really don't take this the wrong way. I don't care for how you see it. This is just a mathematical principle.
No, I do appreciate. I appreciate you actually doing this. Definitely, 100%, because this is exactly how the argument is, and that is the opposing view. Is that does go down and it does get blocked by that foreground wave.
People don't understand how angles work. They don't understand geometry. Do you understand geometry?
Okay, I'm not as well as you. Definitely not. Right.
Do you understand the fact that, to go back to this diagram here, these objects will never drop to a point, like, because they're not changing in height, no matter how far it is, you never have to have a negative elevation angle to observe the top of them. Do you understand that?
Yes, in geometry.
Yes.
100%. Now you are distorting that geometry with perspective.
Do you understand that if the waves are not as tall as the observer, he will always have to look down at the waves in order to observe them, no matter how far away they are? Do you understand that?
Sure, but there is a difference to that which is highly relevant with that black swan photo, where, put it this way,
black swan photo, I can explain it to you, but
no. I'm going to explain the alternative, the one that is blocking. Now, the observer height is 1 foot, and if you look back on the historic on Noah on the same date, there are recorded waves which are 4 to 6 feet. So if you're 1 foot, that is going to have a net effect of blockage. You can't tell me that doesn't.
What I'm pointing out is that if we were to go back to this happens even when the waves are beneath the observer, because you're on a clear, calm, sunny day. There's no waves that are going above the observer. It's just a sunny day. You're on the beach. You're observing a ship that's going way off in the distance. It will drop beneath what's you previously considered 0 elevation angle, even when you can still see it. That's not possible on a flat Earth because the waves are not tall enough to block the top of the ship. Because they're not as tall as the ship, they're not taller than the observer. You always have to look down at them, and you always have to look up at the top of the ship. Even when all that is true, this still happens.
I would agree with you geometrically. Okay, I would agree with you geometrically, but we do not see, and we are not recording these observations in geometric view. Put it this way: I've got a row of lampposts going off into the horizon. The
Sure.
bottom of those lampposts appear to rise up towards the horizon. So one's at 45 degrees and one's at such and such degrees, 80 degrees, 90 degrees. Yep. So
Okay.
they're appearing to change in my 2D picture that I've now taken. Yeah. It's
Let's go
only
into this. Do
go
it
on.
your way. Let's look at the bottom of those things. You will always have to look down at the ground in order to see the bottom of these poles. Yes or no?
Yes.
No matter how far away, you will never have to look up to see the bottom of the poles. Do you understand
No,
that?
but they appear to rise up, even though they
appear to
don't in reality.
Never go to a positive elevation angle. Do you understand?
No, yeah, I understand that 100%.
Similarly, the top of the poles, you will never have to
We're
look
not going-
down to see them. Do you understand that much?
Yes, I understand that from a
Therefore, no
geometric
matter
point
how
of
tall
view.
something is, even if they appear to converge on the horizon, nothing that's beneath eye level will ever be able to obscure something that's above eye level on a flat Earth.
Okay, well, put it this way. Let me try and explain it one last way, and I think I'm going to yield. I'm going to
Okay.
yield as you have done a good enough explanation for me to yield that the whole point. The whole
All
point of that. Yeah. I mean, I'm not proud enough to say, yeah, I'm right, you're wrong. Shut up, because you've done an amazing explanation and you have gone right the way through it. However, the point is that your perspective from a flat earther's point of view is distorting geometry. And there needs to be a reverse engineer, let's say, of that distortion.
Okay.
And the distortion is you've got a limited amount that you can resolve of the floor. Everything beyond that point will get blocked bottom up.
Sure.
And let's say a better way to put it is because your floor appears to rise to eye level, the wave that I'm talking about that's doing the blocking is at your horizon. So
Sure.
you've got mean sea level, and then you put a wave on top of that. Now anything beyond that's going to get smaller and smaller and smaller. You're not going to see the bottom shrinking, but you are going to see the top going down, 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 appearing to disappear over a curve. And then
Let's visually represent what you just said. Okay, let's do that right now.
Let's do that, and then we need to start wrapping it up.
Enough? Yeah. Okay.
I'm not rapping after all this, for God's sake.
And neither will I. There are limits on freedom of speech.
Get
As
your
further away, it will appear to go further and further until it converges on a horizon.
Sure.
Now, if you're above, if your observer height is not 0, if it's greater than 0, so let's say you got 1 meter observer height, that horizon will not be at eye level. It will be slightly below. So, therefore, anything that's above here will never get obscured by something that's here, because on a flat Earth, what should happen is that this will get further and further, or from where it's originally at, and will get closer and closer towards that center point, but it will never go beneath it. Similarly, something that's beneath eye level will get closer and closer to the horizon, but it should never exceed it either, because for that to happen, it would have to be like floating in the air, which is not what we're describing. We're describing things on the surface. No matter how far away it is on a flat Earth, something here does not obscure something here.
Yeah, no, I agree. I agree with that bit, but
top of your
what
ship, it gets closer and closer and closer, and goes beneath eye level. That shouldn't be possible on a flat Earth. That's, in fact, I shouldn't say shouldn't be. That's just not possible.
I don't think you're getting what I'm saying. I don't think you're getting what I'm saying. Where, I mean, it may be completely off key, but the flat earther's point of view is that there is a limit of the floor, the wave is there, and then there's a ship. Let's say before the wave, just before the wave, it breaks that wave, and then the back of the ship, it's a 1 meter wave. It covers only 1 meter of the ship. We'll
Right,
agree
but
on that, yeah. If you're 1 meter, yeah, if you're 1 meter, there's a 1 meter wave. It's just gone through it. There is now a 1 meter wave blocking the bottom of that ship. Let's freeze time on everything apart from the ship. Now, keep that ship going out, out, out. You have still got that 1 meter blockage, but now double the distance, it's blocking 2 to 4 meters. You understand what I'm saying? As it keeps on going, it's blocking more and more, and that is the net effect. Is it appears to drop down.
The actual physical distance it blocks, this D, that doesn't change. The angular resolution or the
It's the angular resolution, exactly that.
down, you're not
yeah,
obscuring more. The amount of the shit that you're obscuring doesn't change. This decreases in size, or at least its apparent size decreases. But you will never see any more of the ship obscured if you were to go off infinitely far.
Surely you would. Surely you
No,
would.
you would.
Because I can hide the moon with my thumb.
Mathematically derive an expression that shows how this somehow becomes this, even though that your eye is here, you're 1 meter tall, these are 1 meter waves, and so you should be perfectly forward, level, no elevation angle, you're only going to obscure this height. Show how this increases mathematically. I want to see that derivation.
Okay, well, we've only got 4 minutes on this. I would love to go through it with you, but it's more of a longer, and I'd like to allow this to be a bid for a hour or maybe hour and a half shorter session to go through this with you and to really understand this. Because put it this way, Jack, what I'm doing here actually, is I'm allowing, not allowing you. It's nothing to do with me doing it, but I'm exploring, I'm telling you directly how the flat earthers are saying it works. Yeah. And what you are doing is combating it perfectly. You are combating it with a demonstration, and you are combating other flat earthers videos that they're putting out today, as I say. Yeah. So you're explaining to people how it would work. However, I would like to present that maths because I think I do have a formula which does work, which can explain the blockage. Okay. However, we'll have to do it another time.
Yep.
If that's okay with you, obviously you don't have to. Don't feel obliged. Do not feel obliged.
Okay.
I think that's a good one to look at. So, a couple things here. Let's see. We've got John Rapp said flashbacks of high school when you were talking about when you're getting into calculus and stuff. Yeah, flashbacks of high school. My question: where does one pick up an eidetic memory? Surely, after 40 years, this info is in there somewhere.
The thing that I find that most high school students struggle with is they memorize formulas, but they don't learn them. You need to be able to intuitively understand them.
You want to derive them.
I know how to write money because I've gone through it, so I'm never going to lose that capacity. I understand how calculus and trigonometry work. I'm never going to lose that capacity. People who just try to memorize formulas, they will lose it after some point because it's just something they've memorized and eventually it will slip away. If they don't actually learn it, then eventually they're just going to lose it.
Yeah.
So that's why I recommend that if you're going to learn math, actually go through it and understand it intuitively. Do the proofs. Prove all of the trig identities that you might need, and that will be your method of learning it without a way of losing it, basically.
Tell me that in 40 years. Or tell John Rapp. GPS is wondering, Gleem, saying CERN
Another X
did not invent the internet. They created the World Wide Web, but the internet is much more than HTTP.
Yawn. It's been so long with GPS. He's like my kit buddy. He sees my name and he gets triggered. He's probably been in the chat, done about 1,000 comments.
He was
saying I love Gleem.
So I don't know if that was what he said. So apparently, and I missed the context of this. Do you think the internet began at CERN, or
it was the internet we know today? Yes.
Okay.
Yes. What it was a flippant comment that they've taken pedantic. Sean Smith, I think it was, and he jumped on the bandwagon for it because he's been embarrassed by me many a time, and he's basically said debate me, and then I've been in Hangouts and not realised that he's been stuck in the background, quiet, because I've been putting a fight up like this on behalf of or with flat earthers, let's say. And fighting off globe earthers, and it's I don't know. You get these people who are obsessed with you, and he's one of them that is definitely daily.
Yeah, whenever I see both you and him in the chat, I see you going at it a lot of the time. So let's see. We've got Johnny B said, I would like to see MC Toon in another Glober versus Gleem and another Denier. So like a tag team or something. Maybe that would be interesting. Tusk, let's see. He's asking, can you ask Gleem, is his dad was a civilian artillery instructor, a soldier, a sailor, or a pool hall owner, or did he run a data analysis company?
3 of them are correct. I'm not going to confirm which because that's pretty stalkish, isn't it?
I
Don't you understand? I will say out of this, by me questioning these things, exactly what I've said to you, Jack, tonight. Yeah, would you ever think in your mind, right? I need to look up who this guy Gleam is and his personal life, and then inbox him about his kids. Would you ever think those was? I get that. I get that trolling permanently. Seriously, and GPS is one of them. Although he does actually keep
this
it
is from
less
Tusk.
personal.
That's from Tusk.
Yeah.
So
But why would
he was
you?
saying,
I mean,
I think he was saying
he's a
these are
CP
things you claimed. I think that
Here
was
we
the
go.
context,
He's a CP. He's a CPO greenie. Yeah, he was a weapons instructor after he served. He done extensions. Yeah. Then he set up or helped set up, or he worked for a telecommunications company and then helped set up an energy management company, of which I then joined, of which we then got bought out, of which I still work for now. That is as much you need to know. That's as much
Okay.
as I expose to everyone.
All right. Let's see. Last one here. Bo Nelson says, please ask Gleem if the sun is the same distance as Polaris by your perspective spreadsheet.
It would be approximately, between 3,800. If you look at Steve Torrance's model, he's got the most well together flat Earth model. He's basically taken 6 different star trail time lapses around the Earth, basically north and south, and he's managed to match them up by putting all the stars at about 4,000 miles up, and the sun and moon hover between, let's say, ebb and flow between 3,800 and 4,200 miles. And what he's actually done is he's not completely coordinate transformed, but made it work using JPL data, JPL horizon data. So it's real world data just projected over an AE map, let's say, and then all the stars and everything put at 4,000. He's gone down into AutoCAD that he's used to design all this to scale, and he's added refraction in there, and he can show the sun setting fine as it would be in reality. He's showing star trails, as I say, matching up.
What caused sunset?
It's this exact combination of refraction and perspective, limits of the floor. It's 3D plane clipping.
Interesting. Yes. All right.
If you look at his refraction, Steve Torrance refraction, there's a racing car driver which normally floods your search. So Steve Torrance, flat Earth, star trails or refraction. He does a 3-part series, and you actually see his model in his map and stuff. And his calculations, you can download it. He's got them in Excel.
All right.
And stuff. So.
Ooh, we got a couple more here. We got John Rapp says, Jack. It's to you, Jack. As much as I enjoy flat Earth debates, you should apply your knowledge to something more productive. This may be a good experience for you, though.
I'm wondering if I should tell any future employers what I do myself.
My employer watches at times and has even sent some super chats.
Can I just quickly add to that and say, from my point of view, 100%, you are doing a good job. You're doing a service, because if you look at it from a relativistic point of view, what you've just done there is explain something that not a lot of globe earthers can do. Okay, when you've got explanations, some people convolute it and wing it, but if you know what you're talking about, as you do, yeah, you've managed to put across a point, and your points clearly, precisely, and backed it up with everything. So, no, salute to you. You are doing a job, because if there are people on the fence, of which I will say I am one, yeah, if there are people on the fence, then you can sway them by going through exactly that. However, I do still want to come back with you on the perspective thing.
All right, so we have one more from Fact. It is a spheroid boom. says, Gleem, if an object is, say, 27 miles high, apparently he's a Weird Al fan, and how can the object on the surface of the water traveling away from you ever be obscured by a 3-foot wave?
Okay, well, I have got examples, but we're too late. Look up Life is Short, bottom up perspective on a flat Earth. And he's done experiments either in hallways, either in across a lake 400 foot. And he's managed to obscure a light that is in the physical water, that is still water. It's a lake. And he is dipping his iPhone in the same water and it's hiding the light. Now, of course, you can say straight away, oh, that's refraction or something. I mean, there's only 1.2 millimeter of curve there, but you can say, yeah, that's refraction. But still, that is a demonstration of something being blocked bottom up with no obstruction in between.
I'll look. I have seen, I think, the one where he had in the hallway, and that Red Pill Philosophy likes to bring up, and that was pretty clear trickery that he was doing there. But so
it's acuity. It's just basically size of the lens and how much light it can let in.
It was the elevation of the top of the lens and instead of the middle of the lens. That was the trickery.
Yeah.
So we got Stringer News 1. Jack, debating flat earthers is actually great preparation for dealing with corporate management.
Okay.
Absolutely.
Good point.
Any of the natural sciences, when you're applying for research grants with private companies, it's a massive pain in the ass because you're appealing to people who usually don't have a formal education in these subjects to give you money.
Yeah.
Have you heard that? What's that one woman's name? The one who started the little pinprick blood tester thing. Do you remember that one?
Yeah.
Yeah. So she got money from people who were very influential but had no formal education, and so you can sell a shit idea to people with money. And you can also give them a good idea and they will turn it down. So believe me, I understand just how hair-tearingly frustrating it can be with these people.
Yep. So John Rapp, so Johnny B was the one that asked about that said you should apply your experience to something else, right? And I said it was John Rapp. Too many Johns here. So John Rapp is saying, sorry, Johnny B gave you the super chat. Good on you, mate. And then one more here from Fact It Is a Spheroid Boom. It says, Gleem, this object is 27 miles tall. So that was the object being obstructed by the 3-foot wave. So
yeah, it's the distance that matters. It's distance. That is the core thing. You've got a limit of the floor, and we didn't even go into the limit of the sky and Polaris, angles to Polaris, but either way, you've got a limit to the floor. Everything beyond that limit is compressed into that 1 pixel, and it appears to as if it's going over a curve. But in fact, it's just moving away from you, and you just can't see the floor beneath it.
All right. That'll have to be another day. Hannah Anderson says, too many Johns, not enough paper. I know some of you might get a little jealous right now. Look at that. We got it. We're not out. So
Gold dust. That's going to be like Bitcoin soon. Keep hold of it.
So,
Toilet coin.
well, thank you very much, Jack and Gleem, for coming on. And maybe we do need to have a rematch or a meeting again or something like that. I will be debating David Munez, I think, or Munez. I don't want to say his name wrong, so sorry if I get it wrong there. At 8 o'clock Central Time tonight on FTFE's channel. So look for that. If you liked this debate or anything, feel free to make some comments on it. And if you think you want to see more of it, make sure you subscribe and click the bell thing. And thanks a lot. And anything either of you want to say in closing?
Michael, you gotta have me back sometime where we can just me, you, and I don't know, maybe Punchy or some of the other guys just discuss some of these physics things, because I'm getting to the point where I have to condense these arguments to such a short length that I leave out a bunch of stuff that I think that should be covered. So
yeah, that'd be good. I like to do after shows. So next week I've got 2 debates scheduled already, so maybe the week after, if I only have one scheduled, we can do that as afterwards. So Cool.
All right, that's it.
Gleem, anything?
I've just got to say, salute to both of you. Thanks for having us on. I mean, I will still fight the cause for the flat earthers in as much as when a globe earther starts winging it and I know different. So I'll shut them down. But in the same way, Jack, you seriously, I said on MC Tunes last stream that all I don't understand in the 5-6 years I've been looking at this scene and entertained by it, it's proper better than EastEnders, I bet you. Swear. But over those years, I've seen so many globe earthers not meet flat earthers on their own ground. So they basically say, yeah, it's due to perspective, and explain exactly what I just said there. But then immediately it's a natural thing. You did actually entertain it straight there and then shut it down, obviously, but you did entertain it. And what they would do is automatically put it in orthographic view and assume that straight line anyway, you can see it anyway, regardless, even if it's gone out of angular resolution. There are many that say, no, you should still see it. And it's impossible, especially if you add a little bit of refraction on it that bends the light down and sinking occurs or something like that. Which again is if you look up in Strabo was one of the first to name sinking as a refraction phenomenon, and he thought it was known by many clever people and scholars and whatnot before him, and as the curve of the Earth, and it was mistaken for not being the curve of the Earth. It was just a bigger refraction phenomenon. Yeah, they just assumed it was a sphere, but you just couldn't see it. It was that big that it just looked flat, appeared flat. But either way, thank you very much for tonight. Hopefully there will be a 2 and we'll explore it more.
Yeah.
But either way, I'd appreciate if I don't want to be next, let's say. You definitely, I'd be watching that stream if you want to go through the physics and break down the debunks or the common debunks of the flat Earth. I'd be watching that stream, put it that way.
Yeah. Well, let's plan on that 2 weeks from today.
Right.
See if we can do that. Cool. All right. Well, great. Thanks, everybody. And we'll see you next time. Bye.